Swayam Prabha. Digital India. Educated India.
So far we have been talking about systems which are liquid and solid systems mostly. Solidification is something which we have talked about, liquid to solid transformations. We also talked about solid to solid transformations, variety of solid solid transformations. Let us start looking at liquid gas and solid gas interactions. These are what we call them as heterogeneous systems, where the moment a gas comes, pressure comes into picture. So far we did not actually bother much about the pressure, excepting in one case we talked about Clausius-Clapeyron equation and how the melting point can change as a function of pressure. We have talked about it, if you remember. Basically we can write dG as VdP minus SdT. Okay, this is one of the Maxwell's equations, the most popular Maxwell's equation. Do you know how does this come? You know how this can be derived? If you simply know that dG is if you can write G as H minus Ts, for example if you write D as H minus Ts and basically do partial differentiation, so you can write it as dH equal to basically dG equal to dH, or you can even possibly write it as basically H is E plus PV minus Ts. If you write H is E plus PV, so you can write dG is dE plus PdV plus VdP minus SdT minus TdS. This is how we can expand the whole thing. So once you have this expression, we basically take the differential of it, and once you do that, we know that dE plus PdV is TdS. That is the basic definition from the second law of thermodynamics, because you know that ds is equal to q by T and dE plus PdV is equal to q. Am I right? That is the heat content. So if that is the case, I can write this as TdS. TdS is q, and if I write it as TdS, this goes off. So what is left out is dG is VdP minus SdT. It is a very very profound thing, and we can express every phase with this expression. So basically it connects the free energy with the state variables, volume, pressure, temperature and entropy. Out of them, some are extrinsic, some are intrinsic. You people know what are the extrinsic variables and intrinsic? Out of these, which are the extrinsic and which are the intrinsic? Entropy. Which are state variables? Okay, entropy. And yes, pressure and temperature are the state variables. Volume and entropy are not. So we can do that. So anyway, so once we can derive this, today let us look at and we use this expression basically looking at for example we can write this expression for every phase transformation. We have done this earlier for liquid to solid. For example, we can write dG of liquid is V of liquid into dP, S of liquid into dt, and we also written that dG of solid is V of solid into dP minus S of solid into dt, and we know that at equilibrium both the free energies are equal. So when we equated these two, we got an expression where basically VL minus Vs into dP should be equal to SL minus SS into dt, and that is where we got an expression called dt by dp is SL, or we call it as delta S by delta V, or we can also write it as delta H minus T into delta V, because delta V by delta S, I am right, you are right, this is delta V by delta S. So, obviously this will become delta V by delta H into T, T comes up, right. So, this is and if you want to avoid confusion we can put the T in front, otherwise this is delta V T. So, it is basically this gives us an idea where delta H is the heat of transformation, delta V is the volume change during transformation, and so the change in the transformation temperature, any transformation temperature for that matter, is related to the pressure by this expression. This is what we have talked about it in Clasher-Clapeyron. Today let us look at sublimation, because when we want to talk about heterogeneous reactions, gaseous things have to be involved. So, let us start with a sublimation as a reaction where there is a gas that is involved before we actually start dealing with solid gas reactions or liquid gas reactions. So, let us look at a system where a solid is sublimating into a gas. If that is the case, then we can actually start writing the expressions for that in terms of the gas, or for the solid again you can use this kind of an expression, and from that we can bring out a few things. For example, if you want to look at let me just see, yeah. So, basically if you want to look at this expression, if you take the gaseous part of it, if you can write this expression for the gas, dg is vdp minus sdt, and if you imagine that there is a chamber where there is a solid which is sublimating at a constant temperature, if you assume that the temperature is constant, then in principle then this term actually vanishes, isn't it. So, if that term vanishes, then we can talk this as nothing but VDP. So, if you want to consider this expression in detail, yeah. So, we can basically write this expression as dP by dt as equivalent to delta S by delta V, which is also can be written as delta H by delta V into T, where this expression, where when we talk about this in terms of delta V, here delta V is basically nothing but V of the gas minus V of the solid, am I right, and usually V of the gas is much larger than the V of the solid, am I right. It depends on which direction you want to look at it. You can look at that way or this way, then both of them become negative, both of them will get cancelled. So, when we assume that this is much larger than this, we can write the delta V can be actually taken as almost this, and when there is a gas, we can always use the ideal gas equation where we can write RT equal to PV. So, we can write that V is actually RT by P, am I right. So, in principle where you have this expression delta V can be written as V of the gas, and V of the gas can be written as RT by P of the gas. So, if you do that, then we can write it as dP by dt as equivalent to delta H by T delta H by T, this remains the same. In place of delta V we are writing it as V, because delta V we are approximating it to V of the gas, because V of the solid is much smaller than the V of the gas, and then this place of V of the gas we can write in terms of RT by P. So basically this becomes RT, okay, P goes here. So this basically means delta H into P divided by RT square. Am I right? Right. So in principle then we can write that dP by P is delta H by RT square into dt. Fine. So this can be basically taken it as d ln P as you can see, if you can further d ln P by d of 1 by T can be taken as minus delta H by R, okay, where you can see that this dt can be brought this side in terms of 1 by T, and if that is the case then we can basically say that if you see how the vapor pressure changes with temperature, it is actually always related to the delta H of sublimation divided by this. So in principle we can say, now if you try to integrate this you can always write that ln P will be equal to minus delta H by RT plus some constant, you call it as A. So in principle that means if we always plot ln P versus 1 by T, if you plot ln P versus 1 by T, you will always see an expression something of this sort, where the slope of this turns out to be delta H by R. So this is how, if one can measure the partial pressure of any gas where a solid is sublimating and there is a gas inside the chamber, and as you change the temperature how this partial pressure of the gas is changing, if you try to measure that partial pressure of the gas as a function of the temperature, you would see that these two are related to this, and the higher the sublimation delta H, the higher this value, the smaller will be the partial pressure. This is expected because if the sublimation enthalpy, the delta H associated with sublimation is very large, then at any given temperature, because you need more energy for the sublimation, so the amount of gas molecules generated from a solid are always going to be lower if the delta H. So that means particularly when we are looking at metals with a higher boiling point, a metal with a higher boiling point basically means its delta H sublimation is very large. That is when actually you will have a boiling point being very high. So whenever the sublimation delta H is very very large, you would say that this material is more difficult to sublimate. So you need to provide more energy for the sublimation to take place, for any solid molecule to be converted into a gaseous molecule. So if that is the case, the partial pressure of the gas that is generated at any given temperature is going to be proportional to that, inversely proportional in principle. So as a result we can say that whenever the sublimation enthalpy is higher, this is also similar to saying that whenever the melting point, I mean whenever the heat of fusion is very large, we can say the metal to melt is more difficult, isn't it? It is as simple as that. You need to, because heat of fusion basically is something to be added to be provided to the solid, so that a solid gets converted into a liquid. So the larger this value, the more difficult for the solid to melt. Similarly, the larger the heat of sublimation, the more difficult for a solid to sublimate. So the partial pressure of the gas that you generate because of the sublimation of a solid is always inversely proportional to this, and the larger this value, the smaller will be the partial pressure. So by measuring the partial pressure as a function of temperature, even if you do not know this, one would be able to get at 4 or 5 different temperatures, you measure the partial pressure of a particular metal vapor in a chamber by certain there are so many methods of chromatography methods are available, spectroscopic methods are available to measure the partial pressure of gases, and if you can do those things then at various temperatures plot it and get a least square fit for that, and from that you will be able to measure this sublimation temperature. Or what is the other method, can does anybody know? If I want to know what is the enthalpy of sublimation, what is the direct DSC is the direct method. Okay. So take a sample in a DSC, provided the DSC can go to the temperature where your sample sublimates. Unfortunately, most of the DSCs go up to, let us say, 1500 degrees or so. The one that we have in our lab goes to about 1500 degrees. So if the sublimation temperature of the material is below 1500, in principle you would see a strong peak associated with the sublimation. Of course, whether it is this side or that side depends on what is the polarity that we are talking about. So but basically sublimation being an endothermic reaction, you get an endothermic peak at the sublimation temperature, and this basically represents the onset of the sublimation. And what does this represent? Anybody knows? In any DSC, what does the peak indicate? Anisha, what does the peak indicate in a DSC? You always know that there is a temperature difference between this and this, they are not the same. So there are two temperatures here associated with, in principle there are three temperatures associated with any phase transformation or any reaction in a DSC. What are these three temperatures? What is the physical meaning of these three temperatures? I take anything, let us say I am melting a metal solid, I get a peak again similar, and there will be three temperatures there. Onset represents beginning of the melting, then maximum
melting point.
Transformation is complete.
Then onset is also a melting point. Where it completes, that is the peak. Then what is the third one? So obviously the first and third are more easy to answer, the onset and the completion. Maximum rate, the peak represents always the temperature where the rate of transformation is the highest, rate of transformation is the highest. So one can, but the thing is in principle whenever you want to do what is called reaction rates, for example any transformation, rate of transformation if you are interested, and what is called kinetics of the transformation. In fact if you have any phase transformation taking place, let us say I take a metallic glass, I am crystallizing a glass. The moment I am crystallizing a glass, I get a peak. I have mentioned to you possibly a number of times, we get a peak like this, am I right? A glass when you start with and then you are heating it, you get something like this. What do we call this? What is that? T, glass transition temperature. Okay. So why this glass transition temperature is like this? Why? It is a second order transition. So glass transition is a second order transition, and what is the characteristic of a second order transition?
Second derivative.
second derivative is
Discontinuous.
discontinuous. What about the first derivatives? They are continuous. What does that mean in terms of some thermodynamic parameters? Enthalpy? There is no
enthalpy involving.
there is no enthalpy involved. There is no enthalpy change involved. Please be careful. Okay. So the delta H for the transformation is 0 and the delta S for the transformation is 0 and the delta V for the transformation is 0. So that's a second order transition. A second order transition will be that where the delta V is 0, there is no change in the volume during the transition, there is no change in the enthalpy during the transition, there is no change in the entropy during the transition. Whereas in the first order transition all these three are discontinuous. So there is a change in enthalpy, that is what we call it as heat of fusion. There is a change in the entropy, that is what we call it as entropy of fusion, and there is a change in the volume, which is what we call it as volume expansion or volume change during melting or solidification. So whereas here no, and then this is what we call it as a crystallization. And if any time you do a DSC, many a times if the delta H involved in the reaction, if it is very large, what kind of transformations are those where the delta H involved is very large? Tell me, when will the delta H involved in any particular change is going to be large? Huh? Explosive reaction, okay, that is a reaction. Let us not talk about reactions here, we are talking of phase changes, change in the state. Whenever there is a change in the state of the matter, then the delta H is large. Solid to liquid, solid to gas, liquid to gas. When within a particular state, if there is a transformation taking place, solid to solid, let us say a precipitation, a Martensitic transformation, or it could be a order disorder transition. So all these things usually, excepting order disorder, because order disorder there is a large delta H negative that is involved between ordered state and a disordered state. As a result, many times the order disorder transitions delta H is very large, so the peak is going to be very large, okay, a big peak. Whereas all other, for example, if I am taking iron, pure iron, and transforming a BCC iron to FCC iron, the delta H is very small, and when the delta H is very small, many a times this peak is going to be very broad, particularly if you are talking about a cold worked material. Some of you, if you have ever done any recrystallization of a cold worked material and do it by DSC, let us say, you get usually a very broad peak, because it happens usually the recovery and recrystallization tend to overlap, and you see a broad peak rather than a very sharp peak. And when you get a broad peak, then you identifying the onset becomes very difficult. The way we identify an onset in any peak is you extrapolate this and you extrapolate this, wherever these two intersect is what we take it as the onset of transformation. So, and whenever the peaks are very broad, if you get a broad peak like this, it becomes very difficult for you to identify. Okay, you may still say that I will do this and then find it out. Some places it is more difficult to see, and particularly in some places where you have two peaks overlapping, let us say. So you will see a situation where something like this. In such a case, what is the onset of this is very difficult to find out. Then what I should do in principle is I should do deconvolution and then make it as two peaks, and then find out the onset for this and find out the onset for this. So under such conditions, people usually consider the peak temperature representing the transformation. Though we know peak temperature is not the temperature where the transformation has actually started, we definitely know the peak is not the temperature where the transformation has started. So but in case where it is more difficult to find out what is the onset, we should do this. Otherwise, for all practical theoretical purposes, onset should be actually taken as the transformation temperature. Onset temperature is the and in case of melting kind of things, the onset and the offset, what is called the offset, the second one, are going to be very close unless you really do very fast heating. When you do fast heating, then the onset to offset there will be differences. Otherwise usually they are very close to each other, and using this information, in principle one can get a lot of kinetic information. For example, doing this, if you do this at different heating rates, what will you observe? Let us say I have a glass, I take the glass, put it in a DSC and heat it at a particular rate, and take another piece of the same glass and heat it at a different rate. Do I get the same pattern? If I do not get the same pattern, what will be the difference in the DSC traces that I get at two different rates? Let us say one is let us say R1, another is R2, where R2 is greater than R1. Now tell me what will be the difference that you will get? Peak will broaden. Anything more? Peak will be shifting. Shifting towards what? In which case the peak will be at a higher temperature? R2. What is the logic?
The kinetics are the transformation rates.
No, to get uniformity it will take.
Yes. The basically it is yeah. Any more arguments? Yeah. Yeah. You are saying something, Anisha. Huh? It is basically the inertia of the system. Whenever you heat a sample at a higher rate, the sample does not transform at its equilibrium transformation temperature, and it transforms at a temperature higher than its equilibrium transformation temperature. This is similar to taking a liquid and cooling it very fast. It does not start melting, solidifying at the normal regular equilibrium transformation temperature. Instead it undercools to a lower temperature and the transformation starts at a lower temperature. Exactly similarly, whenever I am heating the liquid, I mean solid, in principle melting point also shifts. The only difference is the shift in the melting point with the heating rate is not as much as the shift in the freezing point with a cooling rate. The reason is also very obvious, that in case of freezing, a new surface has to be created. So there is a activation barrier, and because of the activation barrier, the system, when it is being cooled very fast, you are not providing sufficient time for this nucleus to be created. As a result, it undercools. Whereas if you are heating it solid into a liquid, then you see that because there is already a surface available, you would see that it does not need that much of an activation as you need it in case of a freezing. So as a result, the shift is not as much as possible, but here it is again a solid to solid transformation. A glass crystallizing is not exactly like a liquid being freezing. Okay. So as a result, you would see there is a significant shifts to a higher temperature if the heating rate is higher. So by basically heating it at different rates, 4 or 5 different rates, what you get is different temperatures, starting temperature for different reheating rates R2, R3 and so on. You will get what is called Tx1, Tx2, Tx3 and so on. So identify for each heating rate what is the transformation temperature. If the transformation temperature is sharp enough, identify what is the onset, otherwise consider the peak temperature. And once you have that, you can in principle plot what is called a Kissinger plot, which is nothing but ln beta by Tx square versus 1 by T, where beta is the heating rate and Tx is the crystallization temperature for each of the heating rate, versus 1 by Tx, if you do, you will exactly get this, and where the slope of it can be taken as Q by R, where Q is the activation barrier, exactly similar to what we have done a few minutes back for vaporization, where we have taken ln P by 1 by T and plotted it. So similarly here you simply take the beta and Tx, tabulate the things at least 4 or 5 different temperatures if you do, because basically to be able to get consistent plot, do a least square fitting, and this is how for any such reaction, whether it is a polymorphous transformation or an allotropic transition or a crystallization of a glass or any other transformation, precipitation, all of them you can use this. This is so called the Kissinger plot. Of course, by the name of the person who has talked about it, which is a very famous. So all phase transformations kinetics are done with this, and this is all what is called athermal kinetics. What do we mean by athermal kinetics? Means as a function of heating at different rates you are doing it. You can also have what is called isothermal kinetics. That means at a given temperature you try to have the transformation taking place. In principle, if the same transformation I do it in a DSC, what we plot is delta H versus temperature. The heat evolved versus the temperature is what we are plotting. You can also plot the heat evolved versus time. Basically temperature, once I know the heating rate beta, okay, what is beta is dt by dt, am I right? So this if I take the temperature and divide it with beta, it should become actually time for me, somewhere it should be related to time, isn't it? So in principle heating rate, if I know, and if I know the temperature axis can be converted to time axis. Hold it at a given temperature, and as a function of time you see how the phase is evolving, and in this process you can talk about how much percentage of transformation has taken place. So here it is onset, here it is complete, and at any given time here you can talk about percentage transformation. It is similar to our TTT diagram. At a given temperature you are talking of onset, I mean start of perlite formation, end of perlite formation. Exactly similar you can do a DSC which is called isothermal DSC and find out how is the fraction transform, and that fraction transform can be correlated to an activation energy. We will not talk about it at the moment because this is more too much of kinetics, but sometime if you are interested we will talk about it. Okay. So this is all about how we can see that a partial pressure ln P of it is related to, we have seen that ln P is minus delta H by RT square, RT not RT square plus A, am I right? And in principle if that is the case, one can also write, if we can write it in the exponential form, you can write P is exponential, some constant will be there, minus delta H by RT. Am I right? Once you have in the ln version we can also write this. That means a partial pressure is exponentially related to the temperature, partial pressure of any gas. That is the reason why the temperature is very important in terms of this. We can also see whether how the external pressure influences the partial pressure. Let us say I have a solid which is sublimating and I put some pressure, the chamber where I have the solid which is sublimating, I introduce some gas, let us say an argon gas, at a certain pressure P, and I want to see how this influences it. If you want to see that, then what we can do is, let us try to do, let us write the expression here. In this case we have a condensed phase, we have a gas phase. For both of them, if we write the dg expression, dg of the condensed phase can be written as V of the condensed phase into dP minus S dt, and because we are again calling it as temperature is constant, in principle we can ignore this. Am I right? So, so in such a case we can write this is the dP. So we can write the dg of the condensed is equal to V of the condensed. So if there is any external pressure, with a change of pressure the d changes with this. Now if we do the same thing with the gaseous thing, V of the gas, okay, multiplied by dP. Am I right? In principle we can write this expression that way, and in such a case we can equate both of them. If we equate both of them, because at a given transformation temperature both of them should be equal, the free energy of the gaseous phase and the free energy of the condensed phase should be same. So we can equate and say V of the condensed into dP should be equal to the V of the gas into dP. Okay. So if that is the case, dP minus d of the partial pressure, here in this case we are using a small p because we are talking of the gas, partial pressure of the gas, and there we are talking of the pressure. Okay. So or we can even do it the reverse way, d small p, the rate of change of the partial pressure of the gas with the external pressure that we are putting is related to the V condensed by V gas. Now if you look at this, this V volume of the condensed phase and volume of the gaseous phase, if you compare, the volume of the gaseous phase is much larger than the volume of the condensed phase. Usually the ratio of it is of the order of around 10 to the power minus 4 at any given temperature usually. So if that is the case, then you can show that the partial pressure of the gas that we have, the sublimated gas that is forming, the change of it with the external pressure that we are introducing is actually very, very small. So the external pressures, why this becomes important is, whenever you are trying to sublimate something, this becomes very important, particularly for those people who want to make nanomaterials by gas condensation techniques. Let us say you take a metal, you want to evaporate and form gas and then condense it and get nanoparticles, and you want to do it at various pressures. You want to know how this sublimate, because the rate of formation of nanocrystals is related to the rate of sublimation, and rate of sublimation is related to this. So if I have the certain gas inside the chamber, and the gas pressure inside the chamber, how does it affect the partial pressure of the gas that is generated because of sublimation? You can see that the partial pressure of the sublimated gas does not get changed by the external pressure to a large extent unless this pressure is very, very large. Okay. So if I take this as a 1 atmospheric pressure, at 1 atmospheric pressure this P changes only by 10 to the power minus 4, not much. So this is something which you have to see, whereas if you look at the previous thing, the partial pressure changes with temperature is very, very significant. You can see here P changes we have also written down earlier, it is exponentially related to temperature, while the partial pressure is exponentially related to temperature, the partial pressure is not related significantly with the pressure that is there. So this are the two aspects one has to remember whenever we are talking of gases coming out of the solids, and how the temperature and pressure, which are the two important state variables, how do they influence the formation of gases from a solid. Okay. So this is the first concept that we need to understand when we are talking of heterogeneous reactions involving gases, how pressure and temperature influence the sublimation, influence the partial pressures. Now once we understand this, let us go ahead with reactions and start talking about how the reaction rates and the thermodynamics of reactions depend on pressures, temperatures and things like that. For that matter, let us simply take up a simple case where A reacts with O and gives you AO. Okay. And you can also call it as O2 and then maybe take it as half of it if you want, and then say that A gives you a AO with 1 half of the mole of oxygen. If you are taking such a reaction, how do we understand the thermodynamics of this kind of reactions? To understand the thermodynamics of that kind of reactions, one or two concepts which we should already know, which we have possibly done it earlier, is one that we already know that chemical, if I want to write G, free energy of anything, we have written it in different ways. Okay. One we have written is what is called XA G bar A plus XB G bar B. You remember this we have written, and we can also write, we have also written G as a function of the complete plus delta G mixing, of course whatever it is, am I right? And in principle we can also write this G as XA into G bar A. G bar A can be written as G naught plus RT ln A of A. Okay. Any chemical potential, G naught is the standard state. Okay. You can call it as G naught, usually put it as A, G naught of A. So the chemical potential can be always expressed as this, and in fact from here you can get the whole expression of this. When you talk of A, if it is an ideal solution, A is equal to X, am I right? And if that is the case, then you see here in the case of delta G mixing, you will see that this turns out to be RT XA ln XA plus XB ln XB, where delta H mixing goes to 0. So basically if you put here A in terms of XA, so this equation becomes actually equivalent to this equation, accepting that this is XA GA. So this will become XA RT ln XA, and then you put another expression for the XB into G naught B plus RT ln XB if you put it. So this whole thing is actually this for the ideal solution. The moment I say it is not an ideal solution, then I can write A as equal to gamma into XA, where you talk of an activity coefficient, and then talk about this, then this gamma actually brings out the delta H mixing. I can put here in place of activity ln A, I can put it as ln gamma XA, and that can be split into two parts, one as ln gamma part another is called ln xa part, and the ln gamma part is what is related to the delta H. So, the delta H mixing is always related to the activity coefficient gamma. So, depending on how you express this equation, whether it is an ideal solution or a non ideal solution, you can express the whole thing in terms of that. But what is more important is you can take that this G bar is G naught plus RT ln AA. If you remember this, we can do a lot of things. You hold on there, we will come back to that as we go along. If you take this expression, which where one solid is reacting with another solid and then giving you reacting with a gas to give you an oxide, both assume that both of them are solids and this is a gaseous phase. In such a case, we can write what is called the delta H delta G of this reaction, okay, and the delta G of the reaction can be taken as delta G naught plus RT ln A of the reaction, okay. And when we say the A of the reaction, so here you have to take it as individual activities of each of them. So, activity of the product, which is nothing but AO, divided by activity of the reactants, where you have activity of A into activity of, okay, O 2, and then to the power half, because this is half is coming. And this activity of O2 we can represent activity in case of gases as partial pressure. So, this becomes PO2. So, you can write this whole expression delta G is equal to delta G naught plus RT ln A of AO into A of A into PO2 to the power half. And in this case, we always know that the activity of solids in their standard states is equal to 1 if they are pure, as long as they are pure. So, if this reaction, if a pure A reacts with oxygen and gives you a pure oxide without any impurities there, then this becomes 1 and this becomes 1, and this whole thing we can write it as, and for any such a reaction at the equilibrium transformation temperature, delta G is 0. So, you can write this as 0 is delta G naught plus RT ln PO2, okay, 1 by PO2 to the power half, right. And this is where we say the delta G naught is equal to minus RT ln 1 by PO2 to the power half. So, this is how. So, if I know what is the partial pressure of oxygen during the reaction, I can actually find out what is the delta G of the reaction without knowing, or if I do not know the delta G of the reaction by some means, if I can find out the delta G of the reaction by let us say doing a DSC. If I do a DSC, what do I get from the DSC? Delta H of the reaction I will get, and if I know the temperature of the reaction, and if I know the entropy of the reaction from the delta H, basically in principle I will be able to get the delta G. So, either measure the delta G or measure the PO2, and you can see both of them are related to each other. And this whole reaction kinetics, reaction thermodynamics are all related to how to relate the free energy with this, and this whole stuff is what we call it as the equilibrium constant or reaction constant. where it is the activity of the products divided by the activity of the reactions. So, this part is what we call it as equilibrium constant K, and people represent this in terms of the equilibrium constants. We will take a few more examples in the next class, where we have not simply one gas, there can be a number of gases involved, and most of our actual reactions in a metallurgy, we deal with a number of gases that are involved and try to see how these reactions change as a function of the free energy and as a function of temperature, and also see as a function of pressure how things change. Okay. With that we will stop now.